Hi, so I'm Amuj Vashne and I'll present our work titled Tunnel Emitter, Tunnel Diode based low power carrier emitters for backscatter tags. This work was done while I was working at Uppsala University together with Lorenzo, who is a PhD student at Uppsala University. I begin my presentation by talking about backscatter communication, whose challenges we overcome with our tunnel emitter system. Backscatter is a low power transmission mechanism that enables transmissions by reflection or absorption of carrier signals. It allows transmissions at tens of microwatts of power consumption. Over the past few years, we have seen a significant interest in backscatter communication, and recent systems demonstrate abilities such as ability to generate commodity wireless protocols compatible with Wi-Fi, Zigbee, Bluetooth, or achieve very long communication range at the orders of kilometers. Backscatter systems require a carrier signal emitter device which provides a carrier signal which is reflected by the backscatter tag to support wireless transmissions. But backscatter systems are also limited by these emitter devices. To explain this, we look at the configuration of backscatter systems. RFID is one of the most widely deployed backscatter system. It works by having a reader device generate a carrier signal which the tag reflects, and the reflected signal is received back by the reader device. This configuration is called a monostatic configuration. However, we find that the reader devices are usually bulky. They generate a strong signal which is about 4 watt in strength, and it needs to be externally powered. Many of the recent systems use a bistatic configuration where the carrier generation and the reception are decoupled and given to separate devices which are separated in space. In this condition, the emitter device is usually a smartphone or Wi-Fi router, all of which are again powerful devices which are externally powered. And we believe this is a key challenge that actually limits the backscatter communication and its application, because these emitter devices are complicated, bulky, and energy expensive, and they often need to be co-located with the tag. To illustrate the challenge of the emitter device, I talk about the long-range backscatter experiments that I did for my earlier work, Loria, that was presented at ACM Census in 2017. Loria was able to demonstrate ability to communicate to long communication range as high as kilometers while consuming tens of microwatts of power at the backscatter tag. Here on the left hand side, we have an image of the experiment setup where we place the carrier generator and the tag over top of a hill. In the next image, you can see me about a kilometer away from the setup being able to receive backscatter transmission. But if you look at in this setup, the carrier emitter was quite powerful. It was generating almost half a watt signal and it was powered by a car battery. So I play the video. And here you can see the setup of a tag and a carrier generator. And here the red light is for the carrier emitter, and the black bag actually has the car battery that is powering the carrier emitter and the amplifier. And here we have the backscatter tag. And this is a constraint that is shared by most existing backscatter systems, which actually require a carrier emitter with an amplifier requiring external power or big batteries to power it. And this is a challenge that we solve with our system, which we call tunnel emitter. So tunnel emitter can support similar communication range as we show with our long range backscatter system Loria, but it can in its simplest form be as small as a small coin cell battery. Here we show the hardware prototypes for the tunnel emitter system that we designed as part of the work. And it is able to achieve this while consuming tens of microwatts of power, which means that it could operate on this coin cell battery for years without even requiring duty cycling. Tunnel emitter is able to achieve this by leveraging tunnel diode oscillators. Tunnel diode oscillators are designed using fascinating semiconductor device called tunnel diodes. Tunnel diodes are a highly doped p-n junction semiconductor device that were discovered and fabricated in late 1950s and early 1960s. These were the first semiconductor device to demonstrate the phenomenon of quantum tunneling, which also led to its inventors to receive Nobel Prize in Physics in 1973. So tunnel diodes, because of this quantum tunneling effect, show a region of negative resistance. What it means is that if you look at the IV curve, of the tunnel diode that we use as part of this work. As we increase the voltage, the current across the tunnel diode increases, but after a certain point it drops even though the voltage increases. And this region occurs at tens of millivolts at the peak power consumption of under 1 milliampere for the particular diode that we use, which means that tunnel diodes are inherently low power device. Further, the negative resistance allows the use of these devices for the design of RF amplifiers, oscillators and switches, which means now we can design these devices at while consuming tens of microwatts of power, which fits in the constraints of small batteries or energy harvesting sources. So while tunnel diodes are these fascinating devices, but we also encounter a challenge in using tunnel diodes, and that is the availability of tunnel diodes. So tunnel diodes were designed and fabricated in 60s and 70s, but over the years their use has dropped, and it can be right now difficult to procure, and we don't know if even any manufacturers make tunnel diodes any longer. But tunnel diodes also can have very long shelf life. For example, Liosaki, who was the inventor of tunnel diode, he found that the tunnel diode fabricated 50 years back was still operational. And we in fact also used tunnel diodes that were fabricated in 60s and 70s and that we got from antique radio electronic stores on eBay. While procuring tunnel diodes is a challenge, but finding information about tunnel diodes is also a challenge. And here, for example, old patents and manuals from early 60s and 70s has been a very valuable source. So here is a stash of some of the tunnel diodes that I have collected over the last few years, and they have been procured from Russia and many other parts of the world. And here are also some of the manual and the magazines which I found very useful in understanding the tunnel diodes and their circuits. We used the tunnel diodes to design a low power oscillator based on the design of TunnelScatter, which we have presented at ACM MobiCom in 2019. TunnelScatter demonstrated a design of an oscillator that, while consuming a peak power of about 57 microwatts, could generate a carrier signal within the 868 MHz band. We show the spectrum obtained from the tunnel diode oscillator in the slide. But the key challenge that we face while integrating the tunnel diode oscillator in the tunnel emitter is that it generates a very weak carrier signal. That means we are generating a carrier signal of about minus 19 dBm in strength. And for backscatter systems, the communication range scales with the strength of the carrier signal, and thus a weak carrier signal might achieve very short communication range, which limits the application scenarios. A weak carrier signal does not impact the range of our system tunnel emitter. We next illustrate why. So if you look at a conventional backscatter system, we have an emitter device which generates a carrier signal, which is then reflected by the backscatter tag. And this reflected signal is then received by a receiver device. In the case of a tunnel emitter system, similar to conventional system, the emitter device generates a carrier signal which is reflected by a tag and received by receiver device. But the reflected signal by the tag also arrives back at the emitter device, which latches onto this backscattered signal, amplifies it, and relays it towards the receiver. Thus at receiver, we find that there are two signals arriving, one from the emitter device and one arriving directly from the tag. And we find that the signal arriving from the emitter device is many orders of magnitude stronger than one propagating directly from the tag. And this is because of a phenomena that we demonstrate for the first time, which we call back injection. This allows us to achieve large communication range despite a weak carrier signal. So back injection phenomena is based on the injection locking. Injection locking is a property where two oscillators with slightly different frequency can synchronize to each other's frequency. And this is demonstrated by many physical phenomena, including tunnel diode oscillators. So back injection phenomena allows the emitter device to become the source of backscatter reflection. And it allows it to amplify the weak backscatter signal by a gain as high as 20 decibel, as we show in some of the experiments that we describe later in the presentation. To illustrate this, we show here a spectrum plot. On the topmost spectrum plot, we see a carrier signal generated from a software-defined radio with a tag backscattering this signal. And we see that the backscatter signal is significantly weaker than the carrier signal. And this is expected as it's a behavior shown by most existing backscatter systems. At the lower plot, we show the spectrum obtained when the backscatter tag reflects the carrier signal generated from tunnel emitter. And we see that because of the back injection phenomena, that the backscatter signal is much stronger than when we were using a conventional emitter device. We also illustrate it through this video. So in this experiment, we co-located a emitter device with a backscatter tag, and we located a spectrum analyzer a few meters away. And we observed the spectrum as we backscattered the signal. First, we had a conventional emitter device, which is a software-defined radio. And as you can see, the backscatter signal is almost not noticeable as well because it's significantly weaker. Next, we replaced the software-defined radio with a tunnel emitter. And you see that the backscatter signals are now even as strong as the carrier signal because of the back injection phenomena.
Tunnel emitter enables carrier signal generation at low power consumption, then enabling operation on small batteries or harvested energy from the environment. Furthermore, back injection enables us to overcome limitation of weak carrier signal generation and achieve then long-range communication. Next, we'll illustrate some experiments that evaluate and demonstrate some aspects of our system. In order to evaluate the gain provided by the back injection phenomenon, we conducted an experiment in the anechoic chamber, whose experiment setup we show in the figure on the right. We changed the location of the backscatter tag with respect to the tunnel emitter and recorded the spectrum through a spectrum analyzer. The figure on the left shows the results of the experiment. Here we see that the backscattered signal from the tunnel emitter is significantly stronger when compared to an SDR. We are also interested in quantifying the back injection gain with respect to the frequency shift of the backscattered signal. We kept the tag at a fixed location from the emitter device and changed the shift frequency of the backscatter signal. As we can see from the figure, the gain of the signal in a conventional backscatter system is not affected by the variation of the frequency shift. Conversely, we found that the back injection gain is inversely proportional to the frequency shift of the backscattered signal. That is, the smaller the frequency shift, the bigger the signal gain. To be noticed, we demonstrated this behavior on 3 different types of tunnel diodes. Because of its low power consumption, tunnel emitter is able to operate without battery while being powered only by the energy harvested by the ambient environment. This capability is challenging or invisible with existing systems. For instance, in this experiment we operated tunnel emitter on a credit card-sized solar cell, and we showed that tunnel emitter can operate on even very low light levels, and as the light conditions improve, which means more energy is harvested, the tunnel emitter remains active often. We trade off stability of the carrier signal in favor of low power consumption in designing tunnel emitter. Next, we described experiments that we conducted to evaluate this aspect. First, we explored the stability of the carrier signal under back injection. We kept a backscatter tag to reflect signal generated from the tunnel emitter and observed the frequency of the carrier signal and reflect the signal over extended time period. As we show in the graph, we find that the carrier signal can drift up to hundreds of kilohertz during few hours. This might require the receiver to be reconfigured to track frequency of the carrier signal. Another parameter that affects the stability of the oscillator is temperature variation. We verified this by increasing and decreasing the temperature of the surface of the tunnel diode with an infrared lamp, as we show in the figure on the left side. We show our results in the figure on the right, which show that the carrier signal drift is directly proportional to the temperature. That is, it increases as the temperature increases. Finally, we quantified tunnel emitter's carrier frequency drift under humidity variation by keeping a constant ambient temperature. We enclosed tunnel emitter within a sealed box together with a humidifier and increased the humidity. Our results show that the carrier signal drift is inversely proportional to the humidity. That is, as the humidity increases, the carrier signal frequency decreases.
Finally, we described the highlight of the evaluation section, which is the experiment where we kept the tunnel emitter in proximity to a long-range backscatter tag. So for a long-range backscatter tag, we used the tag that I had designed as part of my earlier work, Luria, which was presented in Census in 2017. And we kept the backscatter tag at a distance of 0.7 meter and 2 meters away from the tunnel emitter. This distance is sufficient for the back injection phenomena. And we expect, because of the back injection phenomena, to achieve a significant or comparable range to what we had achieved in our earlier work presented at Census. In this experiment, we had also powered the tunnel emitter on small batteries that are used for hearing aids, the PR70 battery. The figure on the left shows the result of the experiment. What it shows is that when the backscatter tag was located at about 0.7 meters, we were able to communicate to the 4 floors of our university building. When the tag was kept at a distance of 2 meters, the backscattered gain decreased, but we were still able to communicate to the adjacent floors of our university building. And this demonstrates that the back injection phenomena and the tunnel emitter allows us to achieve comparable communication range while consuming much lower power for carrier signal generation. We also did an experiment where we replaced the backscatter tag with a tunnel diode based tag. A tunnel diode based tag allows reflection of carrier signal with a significant gain. And this allowed us to enhance the back injection range. And we were able to communicate to multiple floors of a university building when the tag was even kept about up to 12 meters away from the tunnel emitter. Finally, in conclusion, we have presented tunnel emitter, a tunnel diode oscillator based low power carrier emitter that provides the necessary excitation signal required for all existing backscatter systems. We have demonstrated that the low power consumption of tunnel emitter can allow its operation even on small batteries or on energy harvested from a small credit card solar cell. Such capability is challenging or unheard on existing backscatter system. The tunnel emitter, despite the low power consumption, allows us to achieve significant communication range because of the back injection phenomena. And as we demonstrated that when operating together with a tag of a long-range backscatter system, it allows us to even communicate to multiple floors of our university building. We believe that tunnel emitter, due to low power consumption and long range, overcomes the key limitation of existing backscatter systems and thus may enable the widespread deployment of many backscatter applications. Due to the lack of time, we have only covered some aspects of our system and some research results. We encourage you to read our research paper and read about other aspects of our system. And with this, I conclude our presentation.